Okay, so last lecture I finished with the general form of the Euler scale hydrodynamic equation. So there was I want to come back to that I had here. Some general principle for what we have to do to get the Euler scale hydrodynamic equation in many body systems. So that will describe for us the evolution from any state that is varying on large scale, or in fact any state that eventually, as we go over time, will start be just varying on large scale. So it should emerge, from almost any situation. And it describes the very large time and very large space limit, where x and t both scale proportionally to each other and are very large. And all you need, so there is a dynamics that emerges, like water, right, in your bath, which dynamics of emerges from all the molecules interacting with each other. And this dynamics is controlled by reduced number of degrees of freedom. That is a crucial idea of hydrodynamics. And then one way of understanding this reduced number of degrees of freedom is by understanding the set of stationary states. So the physical idea is that locally the system relaxes and becomes almost stationary, both in space and in time. And all we have to do is understand what are all the possible stationary states. And then we see that locally, if you just observe local observables, there will be one stationary state for every point in space-time. And then we determine the dynamics of these stationary states by writing the conservation laws. So principles like that. In order to get the stationary state, we have to determine all the conserved quantities. Once we have that, we construct the stationary state, which are formulae of Gibbs form. Once we have that, we have to evaluate the densities and the currents. And in fact, we just really need to evaluate the currents as function of densities. So there is this current function that appears. And once we have that, we write the Hydro equation. This is the emergent dynamic. So this is a recipe, if you will, right? It's a recipe. I haven't proven it, and there is no mathematical proof of that in any non-trivial interacting non-integrable model. There is no, it is a open problem of mathematical physics. Now, you can apply it for free particles, and for free particles, you can prove that the resulting equation is correct. Okay? In free particles, the set of conserved quantities is the momenta. And the conserved densities, local conserved densities, which are functions of local entropy maximized states, they are function of xt and momenta. And these characterize the function of momentum for given xt characterized the generalized Gibbs ensemble that describes local relaxation for free systems. So generalized Gibbs ensemble, really all it says is that you have some distribution of momentum of these particles, so some distribution in momentum. So they are in relaxed state of a free system. The particles are distributed homogeneously in a way that doesn't change in time, but you can have any function distribution of momentum. And so then there's a function of momentum that appears, and that's this distribution. And then the currents are functions of these conserved densities. In a relatively simple way, it's just momentum times the conserved density. So you just have to multiply by the momentum and you get the current. And this is natural because particles go freely. So if particle has momentum p, mass 1 has velocity p, and that gives you the current. If you know how many particles of momentum p there are, you multiply by p, that's the current for that momentum. So these are the currents for the modes for the conserved quantity of momentum p, p times rho of p. And then you put that in the equation and you get the collisionless Boltzmann equation. And that's indeed the correct equation for free particles. Okay. So locally it looks homogeneous, and then all you can have is some distribution of momenta because all momenta are preserved. And this local distribution of momentum then changes slowly at large scales in space-time according to the Hydro equation. which is basically collisionless Boltzmann equation. If you do interacting non-integrable Galilean models, you just have three conserved quantity: number, particle, momentum, energy. So locally, you're going to have certain number of particles, certain momentum, certain energy, and otherwise it is homogeneous locally and has maximized entropy, so it has reached this Gibbs state with these three conserved quantities. And then, because of Galilean invariance, there are still some simplification. So the current of particle is just the momentum density. The current of momentum, well, there you don't know what it is, depends on the model. It's some function, but it's a function of the particle density and the energy density plus something that is determined by the momentum density. And it's just determined by Galilean shifts, by Galilean boosts. You just shift to the rest frame by essentially shifting your momentum of all the particles by the average momentum, which is Q1 bar. Okay? And once you shift to the rest frame, what you have is the pressure. The current of momentum is the pressure in the rest frame. Once you know the pressure, then you know the current. But you have to calculate the pressure. So you have to calculate the momentum current in whatever model you're given. And then the energy current is again determined by this pressure and by momentum density, again via Galilean invariance by using Galilean boost. So there is one function of two variables to know. And once you know it, you know the whole model. And I mean, you know the large scale dynamics of this model. Okay? So reduce degrees of freedom, you have just three functions, and what determines the model is one function of two densities, and that's it. Okay, so these are two particular cases. Okay, now the one thing that was important was these relaxed states. Actually, I like to call them maximal entropy states. These are states that maximize entropy, but that concept is a little bit is what you would find in standard textbook. You write, say, von Neumann entropy. You maximize it with respect to the charges that are conserved, because these charges are conserved, when you relax, they take the same value, so there are constraints on what's happening in relaxation. If you maximize von Neumann entropy, you get Gibbs state. Of course, the question is, why do you have to maximize von Neumann entropy, and why not some other entropy? So this doesn't fully explain, okay? But perhaps the best explanation is that these states are the ones, they are all the stationary states that are, so maybe I go there here, gave some explanation there, right? So the relaxed states, I complete lectures of yesterday, all the stationary state stationary in space and time. So it's normal because locally things have relaxed and nothing moves too much in space and time locally. Stationary state such that correlations vanish fast enough in space. In other words, local observables at different points in space, which are far apart from each other, are not correlated. Now, there are states where these are correlated, but it is natural, physically, it's just physical intuition, let's say physically, it's natural that when the state has relaxed, things decorrelate. They're not correlated anymore, things have mixed enough, there's been enough time going on so that things have all mixed, that correlations between observables decay fast enough. This was what I had written there, correlation decay fast enough, right? So the connected correlation functions, the average of the product minus the product of averages, goes to zero fast enough. And so the notion is that, the principle is that you have to find all the stationary states, space-time stationary states, such that their correlations of local observables decay fast enough. And the so-called, it's sometimes called ergodic principle. A lot of things are called ergodic principle. But one ergodic principle is that these states are nothing else but the Gibbs states for constructed out of all the extensive conserved quantities. This is the idea, right? The ergodic principle, put this in quote, these are all Gibbs states constructed using the extensive conserved quantities. So there is a connection between extensive conserved quantity and decay of correlation. So exponential minus sum over I beta I qi, with qi being extensive, means that that state constructed out of this Boltzmann weight has decaying correlation. There's a connection between extensivity of conserved quantity and decay of correlation functions. Now, because the more precise mathematical form is that the extensivity of a conserved quantity is a notion that is state dependent. So the proper way is to understand these states as being, these quantities as being tangent, describing the tangent space to the manifold of stationary states, such a way that they allow you to go from one point in the manifold to another point in the manifold. So more precisely, what you say is that if you have a state, you have a state, okay, sorry. That depends on some parameter, beta. Its variation, tangent spacing variation. So the variation with respect to that parameter is given by the conserved quantity. So if I have an operator, an observable there, it's going to be given by QO connected. And this is, this is a natural consequence. This is a general property, but it's natural consequence of this exponential form, right? If I do dd beta of trace exponential minus beta q, and then I put an operator and divide by trace exponential minus beta q, right? Maybe I should put minus dd beta. What I get, I have to do the derivative in the numerator and the denominator. If I do the calculation correctly, I get indeed the average of q times O in that state beta connected. So this is the average of O in the state beta. So I get the average QO connected. In other words, I get QO minus QO. And this is the way in which conserved quantities, Qs, describe small modification of a stationary state. And then mathematically, they span the tangent space of the manifold of stationary state. Right? So this little calculation kind of explains these words. Right? But it's kind of a more general principle that you define variation of stationary states by insertion of extensive conserved quantity. So this is a relation between extensive conserved quantities and stationary state, and extensivity and decay, fast enough decay of correlation. Right? Now, all this stuff is it's a bit formal, and unfortunately, the whole theory is not super well developed. But it's something that I haven't put in my notes there, but something that you can find in some of my papers where I start developing that and try to understand how these states defined in that way represent or can describe thermalization. I'll send you a file with a reference on that. Okay, but it's a bit formal. So it's not super practical, but it tells you at least what is actually happening, okay? What is actually happening and why you need extensive conserved quantities, defined in the particular way that I did at the beginning, at the last part of last class. So the particular way was this way, right? So with Q square goes proportional to system size, right? So there's all these connections. Now this is so now we have our maximal entropy states or stationary states that have decaying correlations, and these describe the local states everywhere, and we have a manifold of such states, and we go along the manifold with extensive conserved quantities, and then we describe emergent dynamics by saying that everywhere in space-time there's such a state. So it's kind of a fiber bundle, if you wish, right? On space-time, you have the fiber of all possible states, manifold of states, and everywhere in space-time there's a different state, and they are connected to each other by the conservation laws. That's earlier hydrodynamics in the most general sense. Okay, now, so there was 4 points that I had there. So that point, I explained extensive conserved quantity. That point, I explained what are these states. This point, I didn't really discuss yet, the currents. Okay? And this is a crucial part of this whole theory, because once we have the currents, then we have the Euler equation. And we have to know what these currents look like, right? As function of densities. We have to know a bit of that. Now, to do the hydrodynamic theory of the Liebig model, the cold atom gases, all I need to do is evaluate the currents in GGEs, which are my maximal entropy states, for generic GGEs for all currents, and put that, in the Euler equation. But before doing that, I want to give you general properties of these currents, because these encode a lot of the physics of Euler hydrodynamics. So it's not just formal thing, Euler hydrodynamics, there's a lot of physics into it. In particular, it's where you find the hydrodynamic velocities, which then when we do integrable system, we can identify them. What are the hydro velocities? It's where you find the type of hydrodynamics. Will it have shock or not? The properties of these functions encode essentially all of the phenomenology of hydrodynamics, of the emergent hydro equation that you have. Okay? And essentially, going beyond Euler scale is modifying these functions in a right, clever way. That's what it will be. Okay, and I will discuss that towards last lecture. Okay. So now, what I want to do in this lecture, first bit of the lecture, is explain this point 3. Evaluate the current in this maximum entropy state. Okay. So I go to my lecture 3. Okay. And this is about currents in maximal entropy state. Let me call them MES. So these are the states occurring after relaxation. So generalized Gibbs ensembles, states constructed out of extensive conserved quantities. So if you go into literature on hydrodynamics, often you will see people will write dt qi, I put a bar, okay, plus dx, some function of all these q's. I put a bar on top to say it's average. It's an average in a local maximum entropy state, and I put a bar in the bottom to say it's a vector. Right, so this is my notation. Okay. They will write that, and they will say, let's try something. Let's try this or that function. Let's constrain it, say, constrained by symmetries. Etc. And then they will say, well, this is my guess for some hydro equation. There are coefficients there that I need to adjust and stuff like that. But in fact, this is not very good because this function cannot be any function. These are there's a set of functions, GI, this is G0, G1, G2, for instance, for Gaussian system, or more if you have more constant quantities. They cannot be just any function. Okay, knowing Galilean invariance, knowing these things already constrain them, but this might not be enough. These functions are very special functions, and their special properties come out from statistical mechanics, from the fact that they are currents of constant densities in maximum entropy states. They're just, okay, these currents depend on the model you have to calculate, but you cannot put any function there. In general, the models interacting, you don't know how to compute them. So people, they don't know how to compute, right? So this Ji of Q, what is that, right? Is the average of the current, which you can put at space-time position 0, 0, in a maximum entropy state that's characterized by a vector of generalized inverse temperatures. And as a function of the average of the Q bar, which are the average of the conserved densities in the same state. So this as a function of that, right? It's complicated stuff. It's hard to compute, but in an integrable system, we can compute, but in general. And so people just put any function there and then try to constrain by symmetries and all that. But in fact, there are many constraints, which encode the physics of early hydrodynamics. And I want to discuss some of these constraints, okay? So the first thing is as follows. This is something that I've kind of even glossed over without really discussing it so much. There's a function that maps the inverse temperature to the conserved densities. It's just given by the average of these conserved densities in a state given these generalized inverse temperatures. This is a function, right, from beta to Q bar. Given the generalized inverse temperatures, given the beta, given the state, I can calculate all conserved densities. I can calculate the average density of particle, of energy, and of momentum, right? But here, what I want for this function there, I want the currents not as function of beta, but a function of the Q's. So I need to invert that function from beta to Q. I need to write Q as function of beta. I need to write beta as function of Q. Right? So there's an inversion of the function that I need to have. That is, can we always write beta, the beta i's, as function of the average Q's? So given the energy density, the momentum density, and the particle density, can I deduce the temperature chemical potential and Galilean boost to a Galilean system? Of course I can, right? It's something that quite general I can. Well, how can I see that I can do that more generally in my general formulation? Okay. So the answer is yes, and goes as follows. You consider this function, how do I call it? I call it for now f, right? You consider this function from beta to q, right? So f of beta is q bar of beta, okay? It's a function with many indices, right? It's a vector function. And you look at d beta I of fj. And the point is that if this mixed derivative is a strictly positive matrix, then the function is invertible. That's from general theorems of invertibility of functions. Okay? What is this thing? So this is something that I will call, and I put a minus there, Cij. It's a matrix, Cij. Okay? So if C is strictly positive, meaning as a matrix, right? Meaning that V transpose CV is greater than 0 for all vector v that is non-zero. Okay? If the matrix C is positive, then f of beta is invertible. Well, at least locally, and if the matrix C is positive everywhere, then it's invertible everywhere, okay? And then I have the inverse, and then, so I can write beta is f inverse of Q, and then I can write J, I say, of the Q is the average of Ji at 0, 0 in the state f inverse of Q. And so I have my current function as function of densities. Okay, so this is the mathematics behind that, right? So I want the current function of densities. Okay. What is this Cij matrix? Well, let us calculate it. If I do minus dd beta I of fj, well, this is dd beta I of the average of qj at 0, 0 in the state beta. And that's something that I just calculated now a few minutes ago. Can do again. So I have the trace exponential minus sum over all k beta k qk, then qj 0, 0 divided by the same trace with an exponential. Okay. So I need to do this derivative. And this derivative I know how to do. I differentiate numerator and denominator. I bring down qk, the total charge. The minus kind of goes away. So this is now the average qk qj 0, 0 connected in the state beta. In other words, if I write explicitly, this is integration over x of the two-point function qk of x. I can put that times 0 and qj 0, 0 connected beta. So this is a total x integral of a two-point correlation function. And what I'm saying is that this thing, so this is C, sorry, this is an I that goes there. This is Cij. If this is positive, then I'm in business, then I can invert the beta as function of Q, so I can find the temperatures given the densities, and I have my current as function of densities. Okay. Well, it turns out that this is indeed positive. So, okay, one can show. So here's the thing. We can show that indeed the matrix C is actually non-negative. It's non-negative, and the proof is like that. You take that expression there, right? And you write it as follows. So the state, so that expression, okay, Cij, you write it as follows. This is the limit when L is very large, and call it L is very large, of integration, say from minus L to L, Qi of x. They are at time 0, so I don't write the time. Is the limit when L is large? It is because the correlation functions decay fast enough, the limit exists. And is that thing, right? And because of translation invariance, it's the same thing as the limit when L goes to infinity of 1 over L integration over x and y of Qi of x, Qj of y connected. This calculation was something that I also said last time, last lecture, because the correlation function just depends on the difference x minus y, and because it is supported only on x near to y because of the correlation decay, I can indeed just put 1 over L and integrate over all of y's. Okay? And now this is a limit when L goes to infinity of, say, Qi between minus L and L times Qj between minus L and L. This is essentially, so if I have I equals J, this is Q square, and Q square is non-negative, right? So if I do sum over I, Vi, Cij, Vj, if I look at this quantity to see if the matrix is positive, essentially to see if it has positive eigenvalues or non-negative eigenvalues, well, I get limit when L goes to infinity of Q dot V between minus L and L times Q dot V between minus L and L, which is just Q dot V square, and that is non-negative. There's a 1 over L everywhere, so I should put the 1 over L is also non-negative. So indeed, I conclude that C as a matrix is non-negative. So it looks like, indeed, I have a positive matrix, right? This is just kind of a direct, immediate calculation. And it's just from the fact that you have space translation invariance, and you get, when you take the derivative with respect to beta of this f, you get essentially a qi, qj. You get the product of two of the same thing. Okay. But I need C strictly greater than 0. So this, unfortunately, I'm not able to prove in general. In fact, the point is that the conserved quantities that you must take, as I was saying, are extensive conserved quantities. They should grow with the system size. Well, so recall that Qi should be extensive. So in other words, the average of Qi between minus L and L square connected should go like system size L. And the crucial thing is that when I say should go like system size L, the proportionality constant should be strictly greater than 0. If it doesn't grow like L, it's not extensive, right? So, and if this is the case, then indeed, from the calculation I just did, that implies that C is greater than 0. So you see I have, in this calculation, have 1 over L and have Q square, okay? And I'm asking for Q square to go like L times something that's non-zero to be extensive. And that indeed shows that if I do have extensive quantities, then C is a positive matrix. So it is important that they be extensive, so not more than volume size of the system, but not less either. Otherwise, you cannot invert the relation between betas and the densities. Okay? So C is a positive matrix. C, this matrix C, as defined here, okay? This is called the covariance matrix. Is the covariance of conserved quantities. And the relation between C and, where is it? This relation between C and the variation of the densities, this shows that the covariance matrix is related to the susceptibilities. So it's also a matrix of susceptibilities. So how much conserved density vary if you vary some of the potential susceptibility. So covariance matrix is matrix of susceptibilities, and covariance matrix, so this thing here is susceptibility. Susceptibilities, this is this. So covariance matrix is a matrix of susceptibilities, is a matrix of covariance of conserved quantities in the state. And it is strictly positive because we have extensive conserved quantities. As a consequence, we can invert, and then we have the betas as function of q's. And then as a consequence, we have our, in principle, our currents as function of q's. Okay? And these currents as function of Q's are called equations of state. Equations of state. Yeah, that's it. Okay, so this is the first thing about this general principle. So it's not just arbitrary matrix, it's not just arbitrary function from beta to Q is an invertible function. Any questions about this?
Benjamin, just to be sure, so you said that if this cumulants, the Q square cumulant grows faster than L, then also it's okay, right?
If it goes faster than L, then we have problems. I mean, here we would have something that is infinite. And then, of course, it's not a problem with having the matrix being zero. It's still non-zero, but it appears to be infinite. Well, perhaps in my calculation, I kind of assume I already something that. So my understanding is that if it goes faster than L, uh, then when you put it in the exponential to describe the state, you get a state that is essentially, well, actually, I don't know. Actually, I don't know. But you don't get a correlation decay maximum entropy state. I think you get a trivial state. Probably you get something that is zero, that has zero correlation or something like that. But actually, I don't know what happens if you put it in the state like that. Yeah.
Okay. Yeah. Thanks.
I do not know. Sorry. Yeah, I don't know. Now, something that I do know is that quantities like that go like L square, so-called quadratic quantities, can be used to describe diffusive correction. So you don't put them directly in the exponential like that, but you can use them to describe the diffusive corrections. You can use them to bound or to control the Onsager matrix, quadratic charge are related to Onsager matrix. So it's like, linear charge Euler scale, quadratic charge Onsager matrix, and higher charge, probably higher orders and all that, right? But you don't put them directly in the exponential, and I don't know what would happen if you put them exponential. But what I know is that the set of extensive one is the set of relaxed state. There are no other states. And so if you put a quadratic charge in there, probably it comes back to one of these states again. It's probably the case, right? It doesn't give a new state. But I don't know how to prove that. Yeah. Other questions? So here we saw that extensivity is actually important, right? It's fundamental in thermodynamics, and we know in thermodynamics extensive charges, are important. Extensive quantities play a fundamental role. So we see how extensivity is mathematically is a crucial element of the consistency of the theory. Okay, so this is the matrix of susceptibility. Now, there's another matrix, and that one is super important, and this is where the physics of hydrodynamics lies in. Okay, another matrix. Now that we have the equations of state, which are the currents as function of densities, so these equations of state, we have that. Okay? We can look at how these equations of states vary. So I can do the following derivative with respect to q bar j of the equation of state ji that depends on all these q bar. This is called the flux Jacobian. Flux Jacobian. Flux because these are currents, average currents, hence fluxes. And Jacobian because I'm taking a derivative of this vector of fluxes, so kind of like a Jacobian matrix that you see when you do a change of variable in the integral with many variables. So called flux Jacobian has two indices. ij, I put one index on top. Because you see, when I took the derivative with respect to q bar here, then I took the derivative with respect to q bar j, the j was in the bottom in the derivative, and because it's derivative, then it becomes on top. That's the situation, okay? It's useful to have the indices in the right position. It simplifies the equation a bit, okay? So aij. Now, what I want to show, so theorem, is that the matrix A with two indices, matrix A, is diagonalizable. Sorry, I cannot write. Diagonalizable with real eigenvalues. And that looks like, okay, mathematical statement. What do I care? It has real eigenvalues. Now that is important. It is important because these real eigenvalues have the interpretation of the velocities of sound modes in this hydrodynamics. Generalized sound modes. So the velocity of sound in air is one of these eigenvalues of such a matrix. And the velocity of the heat mode, which is when you are at rest frame, which is 0, is also one of the eigenvalues of this matrix. So if you heat something there, the heat will not go anywhere. It will stay there and slowly expand. It stays there, velocity 0. Well, if you heat somewhere and there's wind, well, it's going to go with the wind. And velocity of heat mode is non-zero, is the velocity of the wind. So this velocity of the heat mode in a rest frame is eigenvalue 0 of this matrix. In a moving frame is eigenvalue of this matrix, which has the value of this moving velocity. Okay. So eigenvalues of this matrix are the velocities of propagation of disturbances in a gas. And I'll come back to why this is, okay? But first I show this theorem. It's a very simple way to show this theorem. And it's based on a beautiful observation. Mm-hmm. And it's the following. I construct another matrix. B has two indices down, okay? And this is A, I, K, C, K, J. So you see how it's useful to have indices up and down, right? So I have some indices that are up and down, like in relativity, okay? This matrix B is, of course, real, this is obvious, and symmetric. B transpose is equal to B. This matrix is symmetric. Now, I took derivative. It's kind of not obvious from what I wrote here, but I've got to calculate it as a physical quantity and to see how I show that it is symmetric. Okay? Observation B is symmetric. To be shown below. Okay, I'm going to show it below. But if we accept that this new matrix is symmetric, right? So B, if I write it without indices, is A times C. Remember, C is the covariance matrix. Okay? So Flood-Jacobian times covariance matrix. Okay? If it is the case, then we can say we can consider the matrix square root of C inverse times A times square root of C. Okay. Consider this matrix. I don't have a name for it, actually. It's just that matrix. Okay. Now, remember that C is positive. So it has strictly positive eigenvalues. So the square root makes sense. I mean, I don't take the principal branch. The inverse makes sense. That has no zero eigenvalues. It's important that C be strictly positive and that it has no zero eigenvalue. Otherwise, C inverse doesn't exist. Okay, so I use that. I use positivity of C. So this matrix is simple to relate to the B matrix because B is A times C. So this is nothing else but square root of C inverse B square root of C inverse. Okay. And now, this new matrix, so let me call it, I don't know, there's no official name for it, B tilde. So B tilde is still symmetric and real. And that's because C itself is symmetric. So if I do the transpose of that, I get C inverse on the left, C inverse on the right. Because C transpose equals C. And this I will write to be shown also below. And so consequence, two things I need to show below, I will do, okay? Consequence. B tilde, since it is real and symmetric, is diagonalizable with real eigenvalues because it's real and symmetric. And so as a consequence, because A is a similarity transformation of B tilde, so A is a similarity transformation of B tilde, then also A is diagonalizable with real eigenvalues. So A itself is not symmetric. It's real, but it's not symmetric. So, eigenvalues could be anything, but it's a similarity transformation of a symmetric matrix. Similarity transformation means that it is related to a symmetric matrix by pre-multiplication by a matrix and post-multiplication by the inverse matrix. This is what it is. This is similarity transformation. Right? So, if indeed B transpose equals B and C transpose equals C, then A is diagonalizable with real eigenvalues. Then I would have proven the theorem. And so what I need to show is B transpose equals B and C transpose equals C. So to show star, this is star, and double star, this is double star. These are the two properties to be shown. Once I have that, I have everything. Okay? But I have that, I have the theorem that matrix A is diagonalizable with real eigenvalues. Okay? How do I show these things? It's not too bad. For the first one, it's relatively simple. C transpose. Let me calculate CJI is C transpose, right? So this is integration dx qj of x qi of 0 connected is the covariance of conserved quantities. Just constructed. So it's that. Okay? But this is also, how do I do that? Because, so this is also the total charge Qj and Qi of 0, okay, connected. Yeah. Because Qj is a total charge, conserved charge, I can bring it the other side. So here, if I'm in a classical system, then I can immediately write Qi of 0, Qj connected. I can just exchange the two of them. But if I'm in a quantum system, you may say, well, operators don't commute, right? They cannot commute. But if I'm in a GGE, where the density matrix is composed of conserved quantities that all commute with each other, then I can exchange it. I can exchange it with the density matrix. In fact, more generally, yeah, so I will leave it at this. Suppose I'm in classical system. So in classical system, or with a density matrix, with the quantum system, density matrix, which is of the form of GG, right, exponential, sum over I, beta I, qi, where all the qi's and the qj's commute with each other for all I and j. So in both cases, I can bring the q to the other side. Okay. And I will consider this case because this is the only something appeared there. These are the only cases that are relevant for what we're going to do. Okay. So then I can bring the q to the other side, and then I have, so I'm going into detail about this computation. So I have qi of 0, qj of x. So you see that already the I and j in this have exchanged, but okay, my integration is on the second instead of the first one. Then I can use translation invariance. This is qi minus x, qj of 0. And yes, and then I can use change of variable x to minus x. So this is qi of x, qj of 0. And this is indeed Cij. So this is the fact that C is symmetric. Now, one thing I should say, which is important, I defined Cij. Actually, and I forgot to say it there. Okay, I forgot. So there's this current there. I defined Cij, covariance matrix, as being the thing that I obtained by taking the beta I derivative of fj. I took the beta I derivative here. And that taking this derivative brought down qi, because the qi is part of this, right? But we should ask the question, what if qi does not commute with some other of the q's in there in the exponential? If it doesn't commute, it's not true that the derivative is just bringing down qi. It's more complicated. And there's a formula, something related to Baker-Campbell-Hausdorff formula. Okay? So already in this calculation, I assumed that all the q's come with each other in the quantum case. If it's classical, there's no ambiguity. If it's quantum, you have to say that the q's come with each other. If they don't, there's a generalization of the covariance matrix, which involves the so-called Bogolyubov product. And the Bogolyubov product is symmetric. Symmetry of the Bogolyubov product is a consequence of something called the Kubo-Martin-Schwinger relation for quantum systems. So the whole calculation of symmetry of C still works. It's just more complicated, technically more complicated because of non-computation. But everything can still be done if the q's don't commute with each other. Okay. And here I forgot to mention that I'm assuming q's to commute with each other in this calculation. Is the case for integrable systems for most conserved charges, and it's the case for all the examples I'm considering, and it's of course the case for classical systems. Okay. But yeah, so just to mention that in the quantum case, I would need to use Baker-Campbell-Hausdorff formula to take the derivative here. I would obtain something called Bogolyubov product for covariance matrix and for all other similar matrices. And then the symmetry will still hold. Okay, so I say that. Okay, so this was the first one. C is symmetric. What about the second one? This is kind of the most interesting. B. What is B? So B, say, BKI. I want to BKI equals BIK. What is BKI? BKI is AKL-CLI, implied sum over repeated indices. What is AKL? So this is derivative of the average current JK in the state beta with respect to the average density QL in the same state beta. And I can do that because I can invert the function beta to Q. Okay. And C is the derivative of the average density QL in a state beta with respect to beta I. It was my covariance matrix related to susceptibility. And there's a minus sign, because dd beta, I need to put a minus sign to get the covariance matrix. And you see now that I have implied sum over L, I can use chain rule. So this is the derivative of jk beta with respect to beta I. So this is the susceptibility of the current. So this B matrix is current susceptibility. And I know by a similar calculation how to do that. So this is now total charge Qi, current Jk, evaluated at 0 in the state beta. So it's an integrated two-point function. Explicitly, right? This is integration dx Qi of x Jk of 0 in the state beta. Now, what do I do with that? The problem here is that I want this to be equal to bik. I want to exchange the indices here, right? I have an I and a k. I want a k and an I. But if I exchange the indices, the I here is associated with Q. If I exchange it, it will be associated with the current. So it's not just moving things around in translation invariance. The I and k are associated with specific observable densities or currents, and I want to change that. How do I change that? And here is kind of the trick. Okay, so the trick is the following: you look at this Qi of x. I can put time here, and Jk say of x. Let me write the Jk of y and s. I want the case t equals s equals 0, t equals s equals 0, y equals 0, but let's look at that in general. It's connected, right? Then I do the following. I say, okay, let me take a time, let me take a y derivative of that. So d dy of this is qi xt dy jk ys. But dy of a current, I can use conservation laws. So recall that the t qk, I should use s, the s qk of y and s plus the y jk of y and s is equal to 0. That's conservation law for the observables. And so, in other words, this thing is now equal to minus qi xt ds qk ys connected. And now I can use time translation invariance. The fact that this whole function depends on t minus s only, to say that is the same thing as dt qi xt qk ys connected. Now I can use again the conservation laws. So this is minus the xji xt qk ys
Can I ask a
connected.
question?
Yes, go ahead, yeah.
So which of these are operator statements and which of these are statements about expectation values? You have
This is, yeah, it's a very good question. So here I'm using operator statement. So you said I didn't put the bar. These are really operator observables, or random variables, or classical, variables of the phase space. Conservation law at the fundamental microscopic level. That's actually crucial, in fact, indeed, right? But the time to accession variance is a state statement. So that's because the state is time translation invariant. That's what I'm using. So this is a crucial property of the local relaxed maximal entropy state, stationary state.
okay.
Yeah. Then again, I'm using operator statement to have conservation law. And then again, the state statement to bring the derivative to a y derivative. So again, state is now space translation invariant. So I use both time and space translation invariance, crucial. Here, this was, I write it, operator statement. So I use twice operator statement and twice state statement, time translation and space translation invariance. Once I have that, it's very nice because now I see that, I write it like that, ddy, sorry, I write the statement like this. I see that the y derivative of this thing, the y derivative of this thing, which is what I was taking out, the derivative of, okay, qi x t j k y s connected, is equal to the y derivative of that thing. So I would say minus j I x t q k y s connected is equal to 0. So the y derivative of the difference of these things is 0. That's a nice statement. You see, I have inverted now the j's and the q's, right? Because this is kind of interesting. The indices stay in the same place. I just inverted j's and the q's. And I used two of the main properties of stationary states, space-time translation invariance, right? So what that means that this quantity that's inside the parenthesis, okay, call it G, it depends on x, well, it depends on x minus y and t minus s by space-time translation invariance. This quantity is y independent. So I can put it at any position, I get the same value. And it should look like a very surprising thing. These are two different correlation functions. One is qi equal to jk, one is ji equal to qk. There's two different correlation functions. These j's and q's are not necessarily connected with each other. Yet when I take the difference, the result does not depend on the position. So g of, say, x and t does not depend on x. It's interesting. And now let me use the last crucial property of the state. What was the last crucial property of the state? It was the decay of correlations. Decay of correlations. Decay of correlation means that G at x minus y going to infinity, and let me take t equals s because that's the thing I'm interested in, right? But I could take different times as well, okay? But equal time, this goes to 0. Yes, G is the difference of two connected correlation functions. Each of them go to 0 by general properties of the state. But since G does not depend on its first variable, that means that G of x in times 0 is equal to 0. So these two quantities are equal to each other. Consequence of the three crucial properties of the state: stationarity in space-time and clustering. So we find that qi x, let's say times 0, jk y, I can put it to 0, okay, connected, is equal to ji x qk 0. It's very surprising. You can exchange j's and q's, but it's a fact. It's a consequence of general properties of stationary states. once I have that, I come back to what I want to calculate, which was that here. And now you see that I can exchange the J's for the Q's. And then I can use again space-time translation invariance, space translation invariance, x to minus x, bring the Q the other side. And I find as a consequence of that, that BKI, which was, okay, so I go a bit around, which was this thing there. Qix jk0, right? Which was integration dx qi of x jk of 0. Now can be brought then to qk of x ji of 0. Note that, there are some few steps there that use this, okay, But when I use this, I exchange not the indices, I exchange the j's and q's. But then I can do the same set as I did previously for the C matrix to bring the Q the other side, commute through, and to change the integration over X, which is on the first variable, to the one on the second variable, and then I get that, okay? So, and this is BIK. So B is indeed symmetric, and C is symmetric, and I have everything. So this is a rather important property. And we see that we use the three fundamental properties that define the stationary states, the relaxed states, so space-time translation invariance and clustering at large distances. In fact, here we didn't need any strong clustering, as long as it goes to 0, no matter how weakly, how slowly the thing works. When we integrate over X, we need stronger clustering like exponential decay and things like that. I will not go into detail of what kind of clustering, so decay of kinetic correlation function one has. There's a whole theory about that. Okay, so this is that. So now we have, this is kind of the main property of the A matrix, the flux Jacobian, that we have shown. And it says that the flux Jacobian is diagonalizable with three eigenvalues. Okay. Now, this is very beautiful, and let me show you why it's beautiful and what it tells us, what it gives us. Okay. So physical consequences of this mathematical thing. And note that this is completely, entirely rigorous mathematically. All operations that I'm doing there, even derivatives respect to beta and all that can be made rigorous, proven, the result as I showed, proven rigorously. There's no approximation in there. Within many different contexts, for instance, in quantum spin chains, there are so many strong results about clustering, decay of correlation, derivative of beta, and electricity, there's a lot of strong results. All of this is completely rigorous in many contexts. Okay, what can we do? Physical consequence. That's kind of the interesting part, right? Well, let me rewrite the general form of the Euler equation. dt qi plus dx, that's function ji of the q's equals 0. Now, use chain rule. Chain rule tells me that dt qi plus the flux Jacobian aij dx q bar j equals 0, with implied summation over repeated indices. Yeah, I just use the chain rule for the derivative, right? Dx of the function is the Jacobian times dx of its argument. Right? So this is called the quasi-linear form of the Euler equation. Quasi-linear form of Euler equation, of Euler scale equation, let's say, right? It's quasi-linear because it is linear in the derivative with respect to q, but it's quasi because, in general, aij is actually a function of all these q's, right? The derivative of this current with respect to the densities, and that's still a function of all the q's. Except if the currents are linear. Of course, if the currents are linear, then the A is just a constant. And remember that this was the case for the free particles. Property of freeness is equivalent to flux Jacobian being constant. In general, not constant, and then you have a non-trivial function of Q's there. Okay. Now, but what we can do though, even if it's so this is still a nonlinear equation. It's difficult to solve. This difficult thing. But what we can do, can consider linear response. Linear response. It's nice to consider linear response to extract the physics of it, what's happening, right? So assume now then that your QIs are some fixed one, QI0. So I put the x and t now explicitly, plus delta QIs of x and t. So this is a constant in space and time. Okay. So this is a fixed background. So you are stationarity, like you have equilibrated. Okay, so the water at the surface of the pond is flat, and then you put a little disturbance. You put your finger in the water, a little disturbance, a little delta Q, and you want to see what happens with this disturbance. It starts moving around. There's a dynamics. If everything is constant, there's no dynamics. You change a bit, it starts moving around. And in a pond, in a lake, very quiet lake, what you're going to see is that you have some little waves propagating out of where you've put your finger at a given velocity. Now, these are the hydrodynamic velocities, and these are wave propagating. So we should find the same thing here in this 1D case, but more general with many conserved quantities. Okay? So we can do that indeed. And perhaps the easiest is to go again to this Ji of Q bar, right? And now this is Ji of Q zeros plus a small delta Q. Well, here is involved the flux Jacobian, right? Ij of these Q zeros times delta Qj. Sum over J's. Okay, and then I put that in that equation, the Hadley equation that's there, okay? And I find that dt delta Q I plus Aij, that depends now on the background only, delta Qj equals 0. Dx delta Qj equals 0. So now delta Q propagates in a linear fashion. So I can solve that, right? So if I start with delta Qi, say at x and times 0 being some vector Vi delta x, then I know how to evolve it, right? So I have some delta function initial variation. Then the result is delta Qi x and t is going to be, how do I write that? Is going to be delta function of x minus a t times the vector v. Delta function of a matrix, meaning that you have to diagonalize it, write delta function of eigenvalues. So let me check, yeah. So diagonalize. So write A is equal to some matrix. Let's say in the conventional notation is R inverse and something that is diagonal that contains the eigenvalues of V. Okay, V1 up to V whatever number of degrees of freedom, imagine degrees of freedom you have. Let me call this D. Okay. R, okay? So these are, so the Vi are the eigenvalues of A. And of course, we've proven that these are real. Okay? So we do that, and so what we find is that Qi x t is some matrix, R inverse, some delta function of x minus, so R inverse I L F minus VL T and R, sorry, R, L, J, Vj. So the indices, that kind of things, that what we see here is propagation at velocity VL. So we make a disturbance somewhere in space. At time 0, my disturbance was at position 0, delta x. So little disturbance there. And as time evolves, maybe I haven't changed color so much, but I can change color. This is time. As time evolves, I get the propagation moving at velocities v1, v2, maybe there too, v3, maybe this one, v4. I get different velocities where the disturbance is supported with a delta function, with some, numbers in front, with some coefficient that depends on the diagonalization matrix, on the initial disturbance. So that tells me about the physical meaning of the eigenvalues of the A matrix. These are velocities of propagation of small disturbances. Right? Yeah. Any questions about that?
And a question. So when you wrote down the replace J with Aij, A times Q, page above.
Yeah.
So why wasn't the spatial derivative of A? Why was that ignored? A little above.
A little above.
Yeah.
Here.
Yeah. So you have Aij, but the derivative does spatial is. Yeah.
This one, yeah?
Yeah.
Yeah. So what I did is the following. Let me just do it. I did dxji equals dji dq bar. Let me call it L, okay? This is the capital J. Let me do it properly here. dji dq bar L times dq bar L dx. Chain rule, use chain rule.
Okay.
And this is what I define as flux Jacobian. Yeah.
Yep. Thanks.
No problem. Other questions?
More question. So for infinite degrees of freedom or infinite conserved quantities, all these matrices are infinite dimensional.
Yes.
So A will have infinite eigenvalues. What these velocities will
Yeah.
represent?
So this is that's a very good question. So let me indeed. So this, if we think about the integrable system, right, is the first thing that comes to mind. It's, well, we have infinite number of conserved quantities. What's happening, right? And this is a bit subtle. And in fact, maybe I can give the example of the free particle, actually, because free particle conserve a lot of conserved quantity, infinitely many conserved quantities, right? What's happening with the free particles? So we have our Ji of the Q's that became Jp, right? I becomes P. Because we have a continuum of conserved quantity for the free particle, where every momentum is conserved. Continuum, okay? So let's take that in mind, right? So we have a continuum of conserved quantities. And Jp was just the form P times the density. So rho of P. Xt, so this is, I don't need to put xt, rho of P. Okay? So this was the current as a function of the density. The density, I call it rho here because it's the density in phase space. Okay? P times rho. So what is A? So now I have Aij becomes APQ, where P and Q are continuous variable. So actually, the correct interpretation is as a integral operator kernel. So now this is a functional derivative of Jp seen as a functional of the density at Q. And we see that this is P times delta P minus Q. So this is what this matrix becomes. Okay, so it's delta function, and what I mean is as an operator that is obtained by integrating against function. So if I do Aij Fj, it becomes integration dq A P Q F of Q. That would be that. Right? The matrix multiplication becomes integration with some dq. Okay, so this is a integral operator, is a kernel of an integral operator. And it's, of course, it's rather simple to see what its eigenvalues are here. Because it's P times delta P minus Q. So the eigenvalue, the spectrum of this APQ as an integral operator is kind of already diagonalized. Delta P minus Q is diagonal, right? Already diagonalized. The spectrum of this is equal to all the P's real number. So the spectrum is all the momenta. Spectrum is the set of real numbers. The velocities are then all possible real numbers. So what does it mean? It means that in a free system, if you do a disturbance here, where you affect all the particles that are in that region. And then there's some distribution of particles, right? They have all possible momenta. And then they are affected, and they will just propagate at their own momentum because everything is free. And so this disturbance will now propagate in all directions at all these velocities for all possible momentum. So if I do space-time thing, and I change color to make it more clear, I will have, so I have a disturbance here, and I will have all possible velocities. That means simply that the disturbance is going to expand in some kind of ballistic way. So instead of going along certain velocities and expanding a little bit, perhaps diffusively, it's just going to expand everywhere. It's going to go along all velocities. And that's what you see. Now, there is a caveat to that. The set of velocities that you see, also that the set of velocities that you actually see propagating from disturbance depends on the state. The spectrum, the A matrix itself, is something that depends on the state because it's defined as average current in the state. So all these things are state dependent, and you may have states where you have not the full spectrum. For instance, I can start with a system of free particles where I just put three momenta. Momenta 0, momenta 1, and momenta minus 1. And that's it. Then I put a lot of particle, but a bit everywhere in space, but I just distribute these three momenta. I can do that. It's a very singular distribution, but it's okay. It's a good distribution, right? And then if I do disturbance, I will just see these three momenta. So in that case, in that state, I would have a finite number of velocities, and I would see something like that, even in the free particle, just because the state I chose just has finite number of velocities. But in general, I would see that, and this general thing, this is also the situation, the generic situation. The generic situation generically in integral models. So there's a lot of conserved quantities, and it turns out that you get integral kernels instead of these hydrodynamic matrices. You get integral kernel, so hydrodynamic integral operators, and these integral operators typically have a continuous spectrum, and these are the velocities that you observe along this continuous spectrum in integrable system. Often, for instance, if you have a relativistic system, there will be a maximum and minimum velocity, the light cone. Or in a quantum chain is also a light cone. So then you have a continuous spectrum. It's not all possible velocities between minus something and plus something. Fermi velocities or something like that, right? Light cone. Then in very specific situation, you may have holes in the spectrum, depending on the state, right? Or you can even construct states like with the hadrons where you just have 3 velocity or a finite number of them. But generically, you have a continuous spectrum of velocities. Yeah? Other questions?
Benjamin, can you just go up one slide up or a bit more up? Yeah. So for the initial state, you wrote delta qi x0 equal to vi delta x. So what was the vi?
Just some, sorry, this is the bad notation.
Because you have the eigenvalues are vi's, right? It's not.
Sorry about that. Apologies. I should have. V was for vector, maybe.
Some other amplitude, okay.
A is good. So, yeah, whatever. So yeah, some other amplitude. Whatever amplitude that you have that characterize your initial disturbance. It's not the velocity. Sorry about that. Yeah. Other questions? So, okay. So this is these are the main things. There's a lot what I can say, but I want to finish now. I mean, the next thing that I want to do, which connects super well with the last question that was asked about what's happening in integrable system, is indeed now work out everything in integrable systems. Get that A kernel, that spectrum, get the J, get the. So I want to do that next time. That's first thing I will do. Integrable systems. And for that, we need to know a little bit about the physics of integrable system. And this it's interesting. It's about the physics of integrability, actually. And the physics has to do with the scattering and the properties of scattering. So I will describe that. And it turns out, surprisingly, we can get completely general equations for the equation of state, for the A matrix, for all that, which appear to be valid in a huge family of many-body integrable systems. Classical quantum, KdV equation, Liebniger, Hadrods, Toda, all have the same structure. And that's because of the fundamental properties of integrability. At large scale, there's a unique emergent structure. And that's the one that I will describe next time. Yeah, that's what I describe this time. Yeah. So tomorrow. Yeah. And I will write some little question problems, and I will introduce the notion of entropy. I haven't had time to, but I will introduce it in these extra problems. So have a look at it. Entropy, how it's defined, some other general properties of this equation of state, now which are very beautiful, but I don't want to go into too much detail. I want to get to the integrability next time. Okay? But I will write this as in the problem sheets that I will send by end of the day.
One other question was, so are there case examples where one actually needs to consider non-commuting constants? I mean, like usually I see like people do, I mean.
Yeah. So kind of slightly separate thing here. So if you take the Heisenberg chain, sum over position sigma x I dot sigma x plus 1 I, sum over I, right? Heisenberg chain has SU2 invariance. So has conserved quantities, has a lot of conserved quantities, it's integrable. But these include Si, which are sum over x, sigma ix Pauli matrices, right? The total spin in any direction is conserved because it generates a rotation around certain axis, and this Heisenberg chain is completely isotropic from the point of view of the spin axis. But these Si and Sj, they don't commute with each other, right? Epsilon I, ijk or something like that. So this with the I, which is the complex number, right? Square root of minus 1. Sk. So they don't commute with each other. So then you have this problem potentially, and you should put these in your GGEs. They are there, right? They are conserved quantities. They are there in general. Now, very often you have states which kind of favor particular spin orientation, so you don't need to worry about that. But you may need to worry about it. So typically in an integrable system, that's how it happens. It's that you have some internal symmetry that don't commute with each other that you need to account for. That's how it would happen. Yeah.
Okay. I don't see any other questions. So, like Benjamin, you sent some one problem set, and I saw the two references. So the SciPost will have this whatever you're teaching. Is that right? The
Yes. Yeah.
SciPost,
So the
okay.
yeah. So exactly. So this the references of my SciPost notes. What I've taught in the first three lectures essentially is there, except that I don't do the example of free particles. But Fabian Essler notes does the free particle example. I think he does the quantum, but it's essentially similar and all that. So he has started with free particles. So combined of these two things, you get essentially what I've been teaching.
Okay.
So the last bit of today with this A matrix and all that, that's developed in my notes. Yeah.
Okay. Yeah. Thanks. Okay, so I think there are no other questions. So we'll see you tomorrow, and I think we'll have a banquet today, which you'll miss. Sorry about that.
I'm sorry. So enjoy the banquet. Enjoy the banquet. I'll think about you when I have my dinner alone in my place.
Yeah. Okay.
Okay. Thank you. Thank you.
Okay. Thanks. Bye.
Bye.